So we got a parallelogram, and OA is the vector A, and OB is the vector B. So those are the only two vectors that we're going to deal with, but they're telling us some ratios. So the ratio of AB to BP is 2 to 1. So that means if this length is 2, this length is 1. And the entire length is 3. So some of the things I want you to visualize with a ratio like that, BP is half of AB, but does it make sense that going from A to B, that vector is the same as going 2/3 of the way from A to P? So when we're working with our ratios, we also have to think, well, if that ratio is 1 to 2, then that whole length would be 3, and then our fractions involved might be thirds. Similarly, we have another ratio. CQ to QB is 1 to 3, so CQ would be 1, Q to B would be 3. That whole length could be 4. So now I've put some numbers as ratios in there. Those aren't actually lengths of those things. They're just ideas for ratios, so you can figure out that this length here is 1/4 of that whole length. So now with those things in mind, we want to find an expression for the vector from A to B. So we're starting at A, ending at B. And we want to use only our vectors A and B. Well, if I wanted to start at A, could you see that I could go back this way and then to B, following our path A to B, and that would be straightforward. This one would be negative A, this one would be B. So putting those together, you could either write it as negative A plus B or B minus A. And since A and B are both position vectors, that's the most straightforward and easy vector to find. Now that we know what A to B is, to go to A to P, we just have to use that ratio. How much longer is A to P than A to B? Well, you could either think of it as, well, I know the ratio of B to P is half the length of A to B, so I could go A to B plus half the length of A to B again. Simplify that all out and get our answer. Or maybe you can already visualize that A to P is 1.5 times longer than A to B. And if you see that, then it makes sense that you get negative 3 over 2A plus 3 over 2B. So with that in mind, I want you to try 3 and 4. Okay? I want you to try to put together OP and OQ. From O to P, you can see that you could go from O to B and then B to P. Well, O to B is B. B to P is half of A to B. Put that together, and O to P will be 3/2 B minus 1/2 A. Going from O to Q, well, you could go from O to C and then C to Q. O to C, because it's a parallelogram, is going to be the same as going from A to B. And then going from C to Q is 1/4 of the way from going from C to B. Well, C to B is the same as going from O to A, again, because it's a parallelogram. So a to b is negative a plus b, and 1/4 of a gives us negative 3/4 a plus b. Now that's not the only way you can get from O to Q. Maybe you went from O to B first and then went 3/4 of negative a. That would have given you the same result. In fact, you can see that right in the answer, right? If I went to B first, there's my plus B, and then I went backwards 3/4 of A, that would get me there as a result. That would have been easier, but it's not wrong. Of course, if you were traveling along the paths that you were given, and you looked at this picture and you say, I need to get to Q, and these are the roads that are there, most people would say, oh, it makes more sense to go to C and then to Q because it's less distance. But as far as the vectors, it doesn't matter which way you go to get there. And now in the second part here, we want to show now what the vector from Q to P is. We want to show that it's equal to 1/4 A plus 1/2 B. Now we already know from before what OQR and OP is. So you can just go from Q back to O and then go from O up to P and get our results. And so we get QP being 1/4 A plus 1/2 B. Now what I said before to some of you is if we imagined point A to be 5, 0 and point B to be 7, 3, and all those ratios still stayed intact, and I said, how far is it from Q to P? If you were trying to calculate these things using your old triangles, cos law, sine law, and distance between points, this could feel like a lot of work. But we just showed that the vector from Q to P is 1/4 A plus 1/2 B. So we could show that the vector Q to P is really 1/4 of A, and A is 5, 0, plus 1/2 of B, and B was 7, 3. I mean, these aren't nice numbers, but as far as fractions go, we're going to get 5/4, and I'll just write it, 5/4 plus 7/2 will be our x coordinate, and 3/2 will be our y coordinate. And if you want to find out how long something is, that's just the magnitude. So the magnitude of QP, and just as a reminder of our notation, we write that with absolute value bars around it. That's just going to be the square root of a squared plus b squared. Well, this first one, if you add those together, is 19/4. So if you square that, okay, the numbers aren't nice, but we get 361/4, 361/16 plus 9/4. So if we add those together, we get, no, that's not right, 397/16, which simplifies. Square root of 397/16. Over 4, yes. Which I think is really amazing and fascinating, because that using vectors to simplify it with the points that we were given allowed us to figure out this length without too much difficulty. Like, none of the math that we went along was really hard math. We didn't have to deal with square roots or any kind of frustrating numbers along the way. And all of a sudden, wow, we get a very complicated result. We could figure out how far it is from Q to P just given the information that we had. In fact, we could figure out every single point on here in terms of those vectors A and B and find out all sorts of things about them from that. Okay. Sorry, I got a little excited there. We'll calm down again. Whew. So we have a rectangle, and one of the points is the origin. There's a picture of it. We have different lengths. O to A is 8. A to B is 6. We're going to make OA be vector A, OC be vector B. Express the two diagonals in terms of A and B. Well, if I was going from O to B, that would be one diagonal, the red one. I would just have to go in the direction of A and then the direction of B. And because it's a rectangle, can you see that A to B is the same vector as O to C? The vector A to B is the exact same vector as O to C. Same thing, O to A is the same vector as C to B. And so if you wanted the other diagonal from C to A, well, you could go from C to O and then O to A. Of course, if you had called the second diagonal A to C and done it that way, there's nothing here indicating which way the direction needed to go, so that would be correct as well. What's the length of O to B? Well, that's just A squared plus B squared equals C squared. And you might have recognized it's 10 right away. If you took OB and added CA, well, O to B we figured out already was A plus B, and C to A we figured out was negative B plus A. Simplifying those two together is just 2A, and since we know the length of A was 8, the length of OB plus CA is just going to be 16. If you imagine it on this diagram, okay? If I started at OB, here I'll do it in a different color. If I started at O and went to B, I'd end up here, right? Then if I added the vector C to A, that would be going back another diagonal here. Can you see that where I would end up would be the exact same length as two of those rectangles put together? And can you see the 8 plus 8 come together? And finally, if you added OA plus AC plus CO, can you see that OA and AC would just get you to OC? And then if you went OC to CO, well, those C's are the same. You'll just get back to 0, and you get this 0 vector right back to where you started from. So at the bottom of the page there are some questions that you can do that'll practice some more geometrical proofs. Hopefully you saw some of the power of vectors in that last question, of how you can do some crazy math relatively simply just by using vector mathematics.